This is Fundamental Problem 9 from Chapter 17. In this problem, at the instant shown, the uniform 30-kilogram slender rod has a counterclockwise angular velocity of 6 radians per second. Determine the tangential and normal components of reaction of pin O on the rod and the angular acceleration of the rod at this instant. So we have our two sets of equations we can use with Newton's second law and either the sum of the moments about point G or the sum of the moments about point O. In this problem, we're going to do the sum of the moments about the fixed point O. In order to do that, we need to know the moment of inertia about point O. So if they don't give me the radius of gyration or the moment of inertia, then I need to go to the table in the back of the book. And this here is a slender rod. So I'm looking at the slender rod, but what they give me here is the slender rod for an axis which is passing through the mass center, or you could do through an axis passing through the end of the rod, but that's not what I have. So I'm going to have to use the parallel axis theorem in order to find the moment of inertia that I need. That parallel axis theorem is equation 17-4. So the moment of inertia about point O is equal to the moment of inertia about the mass center plus m times d squared, where d is the distance between the axis that passes through the mass center and the axis that passes through point O. So the moment of inertia about an axis which is passing through the mass center for the slender rod is 1/12 times ml squared, where L, you can see from the picture, is the length of the rod. So this is 1/12 times the mass of the rod times the length, which you can see from our diagram here, is 0.9. So this is the moment of inertia about the mass center. And then I want to find the distance d here. And let me draw a little picture. We have our rod, and the total length of the rod is 0.9, which means the mass center is at a distance of 0.45 from the end. Actually, I want to do this end, 0.45. Then I have point O, which is at a distance of 0.3 from this end of the rod. So this is 0.3. This distance here, that is the d that I want in this equation here. And that would be 0.45 minus 0.3, that is 0.15. So for my moment of inertia, this is the mass times d squared, that's 0.15 squared. And the mass is equal to 30 kilograms. So if you plug everything in here and do the math, you get 2.7 kilograms times meter squared for the moment of inertia about point O. So now we can do the sum of the moments about point O is equal to the moment of inertia about point O times the angular acceleration. So in this problem, I have the couple moment of 60 newtons times meters, and that's going in the positive direction. So this is 60. And then I need to ask myself if I have any other forces acting on the rod. The forces that are acting at point O would give me 0 because I'm doing the moment of inertia about point O, but I also have the force of gravity acting on the rod that acts at the center of the rod, and we already figured out the center is a distance of 0.15 away from point O. So this distance is 0.15 meters, and we have a force of gravity acting down here, which is m times g. And that causes rotation in the negative direction. So this is minus the mass, which is 30, times g times this distance, which is 0.15. And that's equal to our moment of inertia, which is 2.7 times the angular acceleration. So we can solve for the angular acceleration. I will let you do that on your own. And you should get the angular acceleration is 5.872 radians per second. And because that's positive, it means the rotation is in the counterclockwise direction. So we found the angular acceleration. Now we have to find the tangential and normal components of reaction of pin O on the rod. So we already used the sum of the moments about point O. The other two equations that we have to use are Newton's second law in the normal direction and in the tangential direction. So let me copy those down. So I have sum of the forces in the normal direction is equal to mass times angular velocity times r sub g, and sum of the forces in the tangential direction is mass times angular acceleration times r sub g. So if I look in the tangential direction, if I go back to the problem here, it said we have a counterclockwise angular velocity. So if the angular velocity is counterclockwise, if you look at point G here, it's rotating this way. So this is our tangential direction. And so when we sum up the forces in the tangential direction, I have the force of gravity acting downwards, and I also have a force at pin O, and I have a tangential component. Let's assume that's going in the positive direction. So I have the tangential component of that force minus the force of gravity acting downwards at the mass center is equal to the mass times the angular acceleration, which I know, times r sub g. And if you go back to figure 17-13, on page 441, they show you that vector goes from pin O to point G. Oh, and they also show you on here, here's the tangential component of the acceleration, and here's the normal component of the acceleration. Always the normal component points in towards O. Okay, so going from point O to point G, that distance is D, which is 0.15. Okay, now I am looking for the tangential component of this force. I can bring mg over to the other side, so I have mass times angular acceleration times 0.15 plus m times g. I know the mass is 30 kilograms, so this is 30 times 5.872 for the angular acceleration times 0.15 plus the mass times 9.81, and you can do that math on your own, and you should get 320.7 newtons for the tangential component of the force. Then, when we look at the sum of the forces in the normal direction, we can find the normal component of that force. Go back to your picture here, and they tell you that the normal component of the acceleration is omega squared times r sub g. This is always directed from point G to point O, because if your object is rotating about the fixed point here, remember that whenever you have, well, back in the first half of this course when we were looking at point particles, when you have the point particle going in the circle, the acceleration in the normal direction is always pointed in towards the center of the circle. So if you pick a point on your rigid body, the acceleration in the normal direction always points in. As long as that point is moving in a circle, it must have a component of acceleration pointed in towards the center of the circle. So that's the normal direction pointed inwards. So that would be here, pointed in towards the center of the circle. That's the normal direction. And let's assume that this component is pointed in the positive direction. And I have the mass times, we're looking at the instant when the angular velocity is equal to 6. So that's 6 squared, and this distance is the 0.15 that I have there. So this gives me 162. So that's 162 newtons, and that's pointing in the positive normal direction. And that concludes fundamental problem 9.